Hey, algebras. Welcome to your Chapter 9, Lesson 4, Day 2 notes on rationalizing radicals. So notice we kind of shifted how we're going to talk about radicals today from dividing into rationalizing. And you'll see as I do some things a little bit differently today that there's a very distinct reason that we're shifting that direction with talking about our radicals that are in fractional form in division problems. Now, again, let's just kind of talk about some of the things that we saw yesterday, okay? So some of the things we saw yesterday, if you have perfect squares in a fraction, well, take their square roots. So the square root of 100 is 10. The square root of 4 is 2. And can 10 evenly divide by 2? Absolutely. We get 5 as our final answer here. If you have perfect squares under the radical, you take their square roots, right? So here we have some perfect squares under the radical. The square root of 1 is 1 for my numerator. The square root of 49 is 7 for my denominator. And boom, 1/7 is my answer. Now, over here, slightly different thing occurring. 96 is not a perfect square. 16 is. Let's take the square root. Let's save that for today. Let's see if 96 and 16 can evenly divide. Let's do that instead so that I can get into the other piece that I was going to kind of go for today. Oh, good. 6. Okay. So even though I've got this perfect square here, what I'm going to do instead is try dividing 96 by 6. Okay, or by 16, because they are both evenly divisible by 16. And because they're both under a radical, then my answer there goes under that radical. Oh, there we go. Radical 6. There's my final answer. Now, I'll talk about that a little bit today as to how that's going to play out, but we'll get there. In these examples, we're not encountering any situations that we've got this radical in a denominator that can't be dealt with, right? That our radicand in the numerator and our radicand in the denominator, they can evenly divide by each other if nothing else. Or I've got perfect squares under the radical, so I can just take their square roots. But remember, yesterday we discussed that we can never, ever, ever, ever leave a radical in a denominator. So yesterday it all worked out that whatever we had in front of us didn't leave a radical in a denominator because we were taking square roots or our radicands could divide by each other. But you and I both know everything doesn't always work out so smoothly when it comes to math. So what if I'm stuck with a radical in a denominator that's not going to divide out in the numerator wise, and it's not a perfect square? Well, I have this little trick to make it a perfect square under my radical. And that is any radical times itself ends up giving me a perfect square radicand. So I did 2 examples right here. Radical 8 times radical 8 is radical 64, and the square root of 64 is 8. So essentially what's happened here is since I'm taking radical 8 and squaring it, multiplying it by itself, the radical and the squaring that I'm doing to it cancel out, and my actual answer is now that the radicand came out of the radical. Notice I'm doing the same thing over here with radical 17, right? When I square radical 17, I multiply it by itself. The radical and the square cancel out, and 17 is what remains. So in each of these, I showed you that interim, the fact that we're getting a perfect square under the radical, but honestly, I'm purposefully making it so that my answer to this is no longer under a radical. All right. Well, what if I'm just stuck with a radical in a denominator, like 5 radical 2? Well, let's force a perfect square in the denominator. We don't care about what's in a numerator. It's just that a radical can never be left in the denominator. Okay, so here we are, never, ever, ever leaving a radical in a denominator. So now what we're going to do is force it. Let's multiply top and bottom by radical 2. So when I do that, radical 2 times radical 2 is radical 4. What's the square root of 4? It's the integer of 2. So I have forced a whole number out into my denominator, pushing that radical up into my numerator to stay there because it can stay there. It just can't stay in my denominator. So because this had to get multiplied by radical 2, this also has to get multiplied by radical 2. So my final answer here, 5 radical 2 over 2. Notice again, no radical in our denominator anymore. Let's do a couple of examples here. Okay. So I've got rationalizing each fraction. No radical in my numerator, a radical 3 in my denominator. 3 is not a perfect square, so let's multiply top and bottom by radical 3. That's the only way to rationalize or get it out of my denominator. Now, radical 3 times radical 3 is radical 9 in my denominator. So we already know that the square root of 9 is 3, so there's my denominator coming out as a whole number. That leaves the top to be whatever this number is times the radical you multiplied in the bottom. 7 times radical 3, that would be a 7 radical 3 as our answer for the numerator. Notice now I come down here, I bring that numerator back down right here, and I look to my coefficients, 7 and 3. Can they evenly divide by each other? Nope, we are done. Let's try another one up here. 12 radical 6. Well, 6 isn't a perfect square, nor is it evenly divisible by a perfect square. We are going to multiply top and bottom by radical 6 on purpose to force this radical 36 in the denominator, okay? Because we can take the square root of 36, it's 6. Now in the numerator, we get 12 times radical 6, that is 12 radical 6, okay? There is no perfect square factor under 6, so there isn't anything that we can evenly divide that by to simplify it. So we bring down 12 radical 6 to the next line, and now we look to our coefficients. Can 12 and 6 evenly divide by anything? Yep, they are both evenly divisible by 6. What is 12 divided by 6? It is 2 radical 6. So notice the radical didn't divide by the denominator. Only the outside numbers, the coefficients, could divide evenly and simplify into a coefficient, one coefficient. See, I've got 1 over radical 5. Radical 5 is not a perfect square, and so I'm going to multiply top and bottom by itself, by that radical 5. Because radical 5 times radical 5 is radical 25. And what is the square root of 25? It's 5. So now we've got a whole number in our denominator. Meanwhile, 1 times anything is itself, so this radical 5 here stays in the numerator forever and ever and ever as our irrational number, but we didn't have a radical left in a denominator. That's the key. All right, down here, radical 2 in a denominator. Well, there it is, again, multiplying top and bottom by that radical 2. So that gives us, now you can, since you've seen the pattern in the denominators, go straight to radical 2 times radical 2 is radical 4. What's the square root of 4? It's 2. So feel free to start doing that. 8 times radical 2 is 8 radical 2. Look to your coefficients, 8 and 2. Can they evenly divide by anything? They're both divisible by 2. So 8 divided by 2 is 4 radical 2 as my final answer. So notice sometimes these will stay in fractions. Sometimes they will simplify and just be some radicals, some irrational numbers. I just quickly want to do J. I've got to stop because my bell is about to ring. If you have a perfect square under the radical in your denominator, just take its square root. What's the square root of 4? So this one was a trick, but I just wanted to make sure I did that. Pause it right here and try E, F, G, and H, please, and I will be back with your answers.
2,000 years later.
Okay, check those answers. See how you did. Now notice again, when we can simplify coefficients, we make sure we simplify coefficients. So when my coefficient 24 can evenly divide by 3, we get 8. Now, 12 and 10 couldn't evenly divide into each other, but could both evenly divide by 2. So that's where we simplify that particular fraction. Think of it as just a fraction and multiplied by this radical 10 that's going to stay in our numerator. All right. Please make sure that you give these a try on 9-4 homework number 2. Let me know if you have any issues at all, and I will see you for talking about how numbers are rational or irrational. All right, algebras, good luck. Have fun. See you soon.